Hi guys, so I'm going to give you a quick walkthrough on what I was doing before in my previous demo where I got Embassy and Rust with on a STM32 chip, but now I basically shifted over to using an RP2040 or Raspberry Pi 2040, and my goal is really less to do with focusing on the microcontroller architecture itself, but it's really more to develop a driver, in this case, for over I2C for a certain chip. So the chip I'm playing with is the rv8803. This is an older crate I did. It was horrible. It was just a dummy, and I really should have never published it. So now I'm marked as published false. This is a brand new API. So until this is fully stabilized and fully tested, I will not be releasing this. I have yanked every other release out there, and just to show you how it's going to work this time around at least. So we have a basic, well, put this, we've got a main struct called driver, and using driver, let me show you what it's going to do here. You can basically use the library, get driver up on this. Well, you can basically instantiate driver over your I2C peripheral. Now the I2C peripheral is standard Embassy, right? It's you have your direct peripheral. You instantiate your I2C instance, and then you get the value, and using the value you can you can basically create a value of driver itself. So in other languages, bear with me, I'm going to sip some tea. In other languages, you would use terminology such as in OOP, class-based. You have your class and you have your instance. In Ruby, you would say you have your methods and instances. In Rust, it's more you have types and values. So this is our driver type, and by calling essentially a constructor, we create a value of that type, and values have lifetimes. Okay, so we have the documentation for my crate up. I basically generated it. Actually, I'm going to use my build script, and a lot of warnings because I haven't cleaned out the latest iteration. What's this about? Oh, these are clippy stuff, right? Reference. Clippy, is it a warning or an error? Oh, these are clippy stuff, right? Don't worry about clippy stuff, that I'll do later on. So we have driver, we have clock data. So what I'm doing here is I set up a struct called clock data. We can set values on this struct, and that's where the set method comes in on the struct type, right? So we have set, it's over mut self, mutable self. So you need to have a value, and only a value that is mutably shared can call set. Right? Sets the date and time. Hundreds is set to 0. Now there's a small caveat here. This is correct. It sets 100 to 0, but that's only on the struct, right? We're not talking about resetting the hundreds register to 0. That's something else actually. So this is the manual, and if we jump over to page 15, I believe. So we have the pin descriptions. Let's make this a bit bigger for everyone, right? There we go. I think that's a good size. Maybe even like this, right? Yeah, let's go bigger so you can see everything. That's a bit too big. Okay. And so if you go, I'll try to scroll slowly, but just so here we go. This is how the addresses work. Oh, they wrap around. Interesting. Okay. So we have the protection of blah blah blah, registered organization, 02. So I'm basically working in this area. Corrupt. Freeze the clock in order to read out process. Okay. Yeah, I've not fully read this document. I really should, right? So, I've just basically been focusing on manipulating the basic registers and stuff. So much stuff in these data sheets to play around with. Okay, so the ones I'm playing with is this set, right? I don't even come to alarms and stuff. That'd be cool. But yeah, flag register, control register. The control register is interesting. We need to look at that in a bit. Actually, let's just look at control register briefly, and then see if I can jump through the results of it. Where's the option to jump through? Does it come on the left side? Interesting. Oh, highlight. Oh, here we go. Sorry, staring me in the screw face. There we go. So 1F. Now, let me get to the control registers. Flag register. I think we can. Here we go. Control. Here we go. So reserved. There's one for reset, and then no reset. Reset is divide chain. This is the important one. 0th bit. And the 170 also to 00. Product. So this is the important one, right? So this is the reset bit in the control register. So if we go to, I think, the update, we do a reset here. So reset is 0 offsetting time to make sure. Let's just do it this way. Need to reset once for 100 update. Let's change that. Set reset bit. Set control register 1F. Wait, control. What is the register I'm using for control? It is. Where did I put the registers for control? Did I put it in reg? Oh, I totally forgot now. Hang on. Registers. Why and where are they? No, let's go back to update. Update registers our. This should take me there. Here we go. Where is this located even? Oh, it's in registers register. Control is 1F, right? And control reset is 0. Yeah, control reset. That's correct. So that description is pretty correct. Set reset bit to 0 in control register to restart hundreds. Is that a good description? Yeah, to reset hundreds register to 00. So here what we're doing is just to quickly walk. We'll come back to this later on, but what's happening here is we're using the I2C bus or the peripheral. I'm saying I want to access the control address, the control register. I'm going to use the control reset address, which is in this case, it's just wrong. It's really a bit value. I'm accessing bit 0. So we're accessing bit 0, and then we're writing a value of false. It's interesting. Value 0, value 1. Why are we writing a value of false there? I think we should write a value of 1 there. Let's see more about the reset. Is there any more? Yes, this might be an older implementation. When the E reset is set to 1, okay. Variable is 1. Elements unchanged. Then why are we doing a 0 to it? Okay, now I should have kept a track of that page. It was control register, right? 1fh. It was, I think it was the 1hf, 1fh. Control register. No reset default. Oh, that's interesting. So then this should be a true. Let's try that. I haven't tried this actually, so we'll see what kind of effect it has on this. Wait, what was my previous comment? It was set after setting time to make sure seconds don't get stuck. So I'm basically trying to get this reset, so it's not to reset. So I think that's the opposite we're doing. To prevent seconds, let's change this. To prevent seconds getting stuck. Verification. I'll leave it at false because it did seem to do. But the problem is when we update, the question is, actually I want to try this and see what happens when I set it to true. Because this is an old thing from an old bit of code, right? Like it's over 6 months old. I haven't tested this functionality really, so let's just run this first and show you guys what it does. So here we go. So that's really annoying, right? I need to figure that out. But anyway, so we're running. It's doing its thing. And wait, it's not doing its thing. It did it for a bit and then suddenly, why is it not advancing? Seconds are stuck. What is going on? It was working completely fine. What did I change? Papa? Oh, right, so it is getting stuck, right? Hang on. Yeah. Right, so I'm going to leave that in because it really did get stuck. So that's interesting. So the getting stuck behavior is true. When you do the update, it does get stuck. So, now it's working. Wow. So that, however old it was, this is correct. So we did verify that. So, hang on, I'm going to take my UB key out because this is getting super annoying. There you go, it's out of the USB-C port, so it won't keep bugging us while I'm doing the cast. So it's advancing, it's great, it's doing its job. And yeah, so there's quite a bit going on here though, even though it doesn't seem like it. So what you're seeing is we're reading values over I2C. It comes in, but then what you're seeing here is something called defmt, deferred formatting. It's a formatter or logging mechanism for embedded. What's happening is it comes through here in the loop where basically got a delay of 200 milliseconds, and then every 20 milliseconds it'll block, and it's actually causing a small LED on board, the onboard LED on the rp2040 to blink, and between each blink we're sending out this debugging information through the debugger, the hardware debugger, into what you can see here from probe.rs. And I basically committed out the chip values, so I can show that to you as well. Whoops, not good. And we can do it again. Of course, now it's going to give a reading on every line, and we can see the temp is in the 24s by not pushing our chip too hard, I think. And it's pretty cool to see the real-time updating. So let's comment it out again and just update again. And we're back to getting the output. So let's just walk through what I've done though. So when you come into this module, we go to driver. We did an update at initially, so every time I'm resetting, I'm forcing it to update to a time. This is a pretty old time. What I'm going to do now is I'm just going to set it to my current time. Let's do it roughly, right? And then we'll roughly synchronize it to right, so we have this one, right? So let's just do 1431. It's going to be tough to synchronize this because it takes a small second to get there, right? So let's just try to hit 30. Yeah, okay, so 3. Let me try it on the 20. Yeah, something like that. Oh no! Okay. Let's try 40 seconds. See if we can just. It's about. Yeah, something like that. 39. I think yeah, we're almost there. It's a couple, few, yeah. Yeah, it's a few millis off. But now we just say, okay, date has been set. I will say, do not touch. Date has been set. All right. So the idea is that once we have Wi-Fi working on this, that we can pull an NTP server and update this clock from the NTP server. So what I'm going to do is I'm going to stop this, and I'm going to run it again. So this time we're not doing an update, we're just reading off the chip. It should be in that ballpark. It is. And I can restart the chip, and you can see that it's restarting. What I'm going to do now is I'm going to power cycle the chip as well. Bear with me, I have to yank out a USB power cord. I need a better local setup for this. Right, and it's powered back up. And we'll run it again, and it should do its thing. So while that is working, we can go back to this and have a poke through the driver. So we have driver. Let's go to docs. I think docs might be nicer way of doing it as well. I'm going to have it side by side. So we have the driver. And I'm going to make this smaller so you can see the logging running in the background. And then driver has a few methods. Now is what we used, we've updated what we used earlier to set the clock. But now is what I'm calling within the function here. Now. And then when we see what comes out of now, what we're doing here is we're using the defmt info level logging, and we're just basically passing the entire struct value into defmt. And I figured out some interesting stuff today on that part. So we come here to now. I'm not super happy with the DSL, sort of, but it does get a job done so far. So down the road I might want to revise this, but the way it's going to work is on now we create an instance here, and that is passed. So that's because we're just going to read the values, right? So we pass that as data to our now constructor. now lives in its own area, well, its own module at least. Now has its own traits for read and yeah, just read, right? The modules, what you call associated method, creates a clock data. So that's just handy. We could have got this from anywhere, to be honest, but that's how I just went with it. So if we go back to the modules, I don't know, do we have now exposed? Oh, we do, right? Now. So now has a new, creates a clock data, right? And then now has the traits, read, and read is implemented like this. That's this same trait here. It's nice to see it showing all the debug, copy, clone, like that. That's actually quite nice. It would be nice if my syntax highlighting had traits in a different color. I need to figure that part. That would be lovely, actually. And then we get to clock data now. So this is the meat of it. So we come here, we grab something called the clock registers, and the clock registers is given the address of the device. And then once we do that, we have to, because we're reading the data off the chip data is stored in BCD, binary coded decimals. So we're going to read the value first, and then we're going to do a BCD conversion from BCD to decimal, and we do it for everything, but not for the weekday. That's because I think we need to break this out from here. And I think what I'm going to do, I'm reduce the zoom level, and let's try and actually just whiz up the page to the registers. Yeah, so let's just take a read of, let's look at some of the other registers. Let's go down. They're all the same roughly, but so weekday is a unique one, right? It's basically single bit value running from 0 to 7. So it's like 1, 2, 4, 8, 16, 32, 64. It can only be a single bit at any given time. They say not to set 1 to more than 1 bit. I think if you do, it's going to make you unhappy till you reset it. But everything else, like even the date, is BCD, right? Month, it's a BCD. Year is BCD. RAM. Interesting. Register all the bits for general purposes, so you can use it for RAM. That's interesting. Let's stuff something there and see what it is. Oh no, not that. This is a RAM address. Like it's a 07H. So wasn't that in like registers? So we can do RAM. Let's just do another one. Call it as RAM. I haven't mapped this fully, so we'll just call it RAM and just call it let's do RAM. What was it? 07H. 0 into 0. Yeah, so this is a higher order, well before 10, right? So this is these are other ones that have not been added to my list. Okay. Well, I did have a 06. Oh no, I'm using the lower end one, 17 for the year. Right. So 7H for RAM. Alarm is for 08. So 8, 9. Oh, interesting. So we have quite a few more here to add, right? Let's do that while I'm on screen. Okay. Let's just flesh out the mapping, right? So we're going to have what's this one? Alarm, minutes alarm. Okay. Oh, I see it's going to go minutes alarm 0 into 08, hours alarm 0 into 09. You know what? I'm actually going to open this up pretty quickly and just do a Vim, and then where are we going? What was the editing? Registers, right? What's the next one going to be? 8. Okay. 08 weekday alarm. So these are another level of stuff. So we can come back to those later on. I don't want to play around with those two, but timer count. I'm going to see what are the lower end registers. There were a whole lot of below 10. 20. Okay, what are the ones that are lower than 10? So it starts from RAM. RAM 7. Weekday timer counter. Weekday alarm, date alarm. Those we're going to leave those for now, I guess. Timer counter, except we just do those. And then timer counter. Control is at 0. What is a 1F, right? I guess there's another mapping for it, right? So, let me look at the extension register. Well, there must be another code for that. No. Extension register. Yeah, let's see this one. Oh, here we go. So it's a 0DH and a 01D. I think 01D is a nicer one. Extension register. I'm going to just do extension and just do 0 into 1D. Right. Whoops. Nope. What happened there? What's the next one? Extension register, control register, flag register. Yeah, this one's a 1E. Flag is going to be 0 into 1E. Okay, so we have flag. These are all the flags. This is interesting. Let's see what it says. So read VF1 says all correct low. EVF alarm, spirit countdown, all updates. So because these are flags that happens whenever there's an alarm or a timer type event. Capture buffer event control. A captured copy of the 100 time in 2 byte code. A captured copy. Seconds CPU. So the seconds register. Why would we need a captured copy? Captured buffer. Okay. Holds a captured value. CP register is cleared when the ERST bit in the case next. ERST bit is set. External event detection. Event control. It goes into the extension register. What is the 2FH? Event control register. Okay. Event control registers. Here we go. Event control is 2FH. EVI pin. So glitch frame bloody version. enable caption. So event control is at 2fh. So let's just do that. Not sure if I want to play with these things anything right now, but event can be 0 into 2fh. Pin the 100-second register is reset at 0. Moreover, the 100-second second register also reset. On the ERC reset. Yeah, this is interesting. So it's kind of like if you want to do stopwatch type behavior, probably something like that. Register reset value summary. So we have these. So we have the second series. Controls with the offset, which is 2ch. Timer counter O. The specific function exists in the it's not going to update and range 110 and vice versa. Okay. Reset values after power on. Always written with an EVF flag. Pins, clock out frequency. Okay. Capture, disable, reset function. Disable, flags. What page is this? This is page 26. It's good to read page 26 for sure. Let me just write down the last one. I think we need maybe the offset probably. It's nice to have. And then we can just do offset 0 into 2c. 2c. We won't. I don't think we just need to do CP. These are just registers, you know, with a copy. Those can be added later down the road. Timer counter and this, that's not super critical right now. So you'll be wondering why I'm adding. I'm just adding just for completeness sake, right? And then if we were to just switch back to VS Code, it's updated. You're gonna wonder, what did you do there, and why do you jump to Vim or NeoVim in this case? It's because, as you saw, I can move around without using the mouse, and I can do quite a bit of stuff a bit easier than having to copy paste in VS Code. So, and then you might wonder, okay, why are you using Vim VS Code? With VS Code, at least I just get this nice little UI, and I haven't added the SVD definition just yet. This file, if I copy this through, you can look at the registers and all that stuff. So that's one thing. The other reason I like about VS Code is you can SSH into remote machines that I have quite a bit in my home lab, and then I can basically compile, edit here, save here, and you're basically accessing another machine. Sure, you can SSH over Vim as well. It's a personal preference. That's about it, right? So now you come here, we can see this stuff is doing its thing there. I want to just switch back to this document. So now we spoke about how you can access the data, but now if we go back to driver update. So we went through now, it comes through, how does it show us the stuff though, right? So that comes through, but then how does the formatting work? How is the formatting nice in the terminal? And remember, this is no standard, without the standard libraries, no std. And so what I'm doing is we have a clock data type. Let's find the struct. If we go to structs, we have clock data. Clock data has these, what you can call getters, right? But it also does format, right? Writes a different representation of format. And this is where things get interesting. So I've got a writer here to help me basically pad the information. So just tiny function here. It basically lets me pad a leading 0 onto these numbers if it's less than 10. And then there's one thing that's not needed here. Let me just double check. Yeah, the buffer clear isn't really needed, but I left it in there anyways. It just basically sets the cursor back to 0, but it's not, and well, by default it's at 2. When you do new, the constructor sets it to 0, but yeah, it's nice to have. Let's just leave a space there. It's easy to read. I'll leave a space between what's been returned and stuff normally. And yeah, so we basically pad hours, minutes, seconds, and day. Now this is something I was writing earlier. I didn't finish up completely, so just to show you what's going to happen to this, really, it's this. Let's drag this across, and I want to open, I think, models to the side. Yeah, this is where I was, I believe. Yeah, so this is what was there before for month, and I upgraded that into this. So this was just like my hacky get up and running approach, but this is far better. Using an enum, the enum has the same mapping for the previous one, was basically the same sequence, matching on the U8, and then spitting out the string, right? Whereas here we do it through the enum, and then we can convert from the enum either back to its variant, right? And then the formatting converts the variant to the str. Yeah, to the str. That's the shed. Well, that's called a str, right? I was about to say string. That's wrong. It's a str. And then we just have in moddisk we have a BC to DEC and DEC to BCD. Now this is something I was pulling my hair over today. This, for whatever reason, I've asked in the channel basically for some help. We'll figure it out. But this doesn't work. This would be nice. So this, using the from trait, these are doing that. I'm just doing this. So we can just say get variant from a provided value. I'll just document the rest and clean up the stuff as I go along, but basically, so I'll be doing the same for this. Anyways, so we come here, and what's nice is, rather than having this whole, mess over here, we just have weekday from the value, and then value converts it to the variant. Then we come here, and we just place the variant, right? And then the variant itself the formatter will call format when it's trying to format itself, and then the variant will convert it to the str, and that's how the str gets formatted to the variant. Now this is just presentational. It is just presentational information down here. I stopped running, didn't I? It's just presentational, nothing else. And it's just showing this as str. So ultimately, when this is being moved from here to another chip, I might use postcard, but there's going to be a new postcard version 2. We'll see. But for my initial play around, it might just be over UART. We'll see. But for the large part, I'm pretty happy with where this thing is at the moment. I'm going to try and do the same test on the STM32, probably using the rack chip, or what are the other ones I have access to, and just double check that this DSL is finally okay. There is one dead file here. I'm going to remove that, and then we have another reg. It is not really doing anything at the moment. It's just a means for manipulating registers themselves, where you can pass a register, and the register itself has the traits on it, and you can just do access register by register. But I prefer to, at the moment, well, I mean, that's something we can do later on, because right now, as you can see, all I'm doing is I'm allowing you to if you go back to the main interface, which is driver, right, all you can really do is you can set the address beyond the default. The default is just, I believe it's the version, yeah, it's the address for this chip, right? So you can change that, and it's also 7-bit addressing, and then you can update the clock, right? You can get the latest value. So when you go to update has a couple methods. So you have settings and update, and then hang on, didn't I set address? Yeah, wait a moment. Set datetime. Why is that not appearing for clock? Oh, it's on clock updater. Where is clock updater? Is clock updater not exposed? Oh, it is there. Methods for clock updater. Set datetime. Here we go. Yeah, this is the one. So updater lets you do a set datetime operation. I think that kind of gels okay for an API. Yeah, I mean, now means you're getting the latest value. Update, yeah, it should be like control reset write register. Or, yeah, this could you do with a better name. But for now, I'm just going to keep this update. So in the same, so the way the update works is the same, right, as now. The module's associated method gives you a clock updater value, and then traits that clock updater need for read, and in this case, write. Use a separate struct for CU. I think I've done that, right? It just has a read on clock updater, but it's yeah, it's a set date time. Okay. And then yeah, but then sorry, so the read write is on the CU, which is clock registers. And then clock registers would, what does clock registers do? I don't walk through this. I haven't read this in a while. Write bit, read register, write register, and that calls write. Yeah, but that's fine. Write register. Yeah, so we come back to, so this is what I had at the start of the video, where, you know, when we're writing, we have to convert the decimal value to BCD. Oh, yeah, that's a good thing to clean up on. Register weekday. I have done that, haven't I? Use enum to convert. No, I haven't done that, have I? Day, weekday, where does that come from? Is that needed, really? Set date time, clock register, clock data. Oh yeah, I've already done that. It's already converted through the weekday part. That's not needed here anymore. And yeah, so we do that conversion. So all of these are decimal to BCD. So what we provide in decimals, oh yeah, let's look at that part. So if we go back here, when we're setting it, these are in decimal, right? So that's the hour, minute, seconds, day of the week, day, month, year, day, month. So for month, as I showed before, we need to have the mapping for month as well. And I think, yeah, that can be done over here, and that'll be done. And that's a quick look at progress on this. And once I finish cleaning this off, I will get started on testing on STM32. Thanks for watching. Bye bye.